Okay, so part 2 of section 2 is still about definite integrals. So integrals that are defined on an interval. How do I calculate indefinite and definite integrals using a TI-Nspire? So this is our main focus here. So example, we're going to calculate the definite integral of x cubed plus x on the interval from 1 to 3. So we want to do this. The definite integral, or defined integral, from 1 to 3 of x cubed plus x dx. So just to recall, the way that we find the integral, aka the antiderivative, is you are going to think of the opposite of derivative. So you're always going to add 1 to our exponent, and then you're going to divide by whatever that exponent is at the point. Okay, so when it comes to polynomials, it's pretty easy. Some of the other ones that we do, there's defined integral rules for those, but we'll do those. Before we do this on the calculator, let's remember how do we do this by hand. So the first thing we do is we find the antiderivative. So that's going to be x to the 4th over 4 plus x squared over 2 plus c. We never forget c because there could possibly have been a variable or a single constant here, not a variable, sorry, a single constant here at the end that once you take the derivative of course becomes 0. And then we're going to take that derivative from 3 to 1. So when we plug in and subtract, you're going to get 3 to the 4th over 4 plus 3 squared over 2 plus c minus, big ass parenthesis, right? 1 to the 4th, which is 1 over 4, plus 1/2 plus c. So when it's a defined integral, you notice what happens to the c's is they are going to cancel each other out when you're doing the math. It's always going to be subtracted. So after we solve this, step 3 is solved, you're going to end up with an answer for the integral of x cubed plus x dx from 1 to 3 is equal to 24. So that's by hand. The nice thing is about our calculators is that we are able to do only defined integrals. We're only able to do defined integrals on the calculator. So what you're going to do is you're going to press home and insert the calculator application or scratch pad. So go to calculate. And then in here you're going to go to menu. You're going to go to calculus and you're going to choose solve. Oops, sorry, I didn't even go to calculus. Go to calculus and we are going to choose numerical integral. Now if you have some of the newer calculators, you are actually able to do more in the calculus option, but we want to find the numerical integral, and it gives you the form. So we're going to go from 1 to 3 of x cubed plus x. You always have to remember to put in what you're integrating in reference to, equals, there's our answer, 24. Okay. So if we do a few examples in the calculator, now on the TI-84, I don't think any of you guys have a TI-84, so I'm just going to leave this part out for now. We've had students in the past who did have a TIA before, so we have to explain that. But anytime you have a defined integral, you are able to evaluate this in the calculator. Okay, so to do all of these problems, the light is not that much better. But to complete all of these problems, you just go menu, calculus, numerical integral, menu, 4, 2, and then you're going to go from -1 for x sine of x to 2 for dx equals, function is not defined. Oh, okay, so I'm glad we kind of went through this error. So the calculator does not understand when you plug in x sine x without the multiplication sign. So anytime you have variables multiply together, you have to put in x times sine of x I'll put the 2 in, dx, and it will give us the answer. Okay, so anytime you have variables or letters that are being multiplied, you definitely have to put that multiplication sign in there. And this answer is in radians because it is trig, and you notice that my calculator is in radians. Alright, I'll let you guys do this in the calculator. It's very easy. You should get a 3.14159 for this one, and for this one you should get 0.886227. Okay? So that's in the calculator. Moving on, discontinuous integrable functions. All continuous functions are integrable. Every function that is continuous can be integrated. You can integrate around a discontinuity if you break up the function into pieces around the point of discontinuity and then determine the total area. Okay? Determine the total area. So you might be missing these words. You just gotta plug them in. So let's consider the following. So if you actually took this function, so right here in our example, f of x is equal to x over x. Obviously, because x is in the denominator, we are going to have a discontinuity at x equals 0. That denominator can never be 0. So let's graph this guy. And you can graph him by hand or you can use the calculator, up to you. But if we graph this guy from -1 to 2, that's basically what I care about, from -1 to 2. So at -1, this is going to be -1. At 0, it is undefined, but up until that 0, you know that we have a function that kind of looks like this. And there's going to be an open circle here, but we do have a function that looks like this. Now, I don't care about the rest of this. I'm just drawing it just to show you that this graph does exist past this point. We are going to end up only focusing from -1 to 2, but this is the graph. So when it's -2, -2 is 2 over -2 is going to be -1. So you're going to be constantly -1. And then after this, for the positive, so obviously when it's 0, it's going to be undefined as well. But when it's like 0.00001, we're going to have 1. If you plug in 1, 1 over 1 is 1. If you plugged in 2, 2 over 2 is 2. And this guy goes off like this. So because here we have a discontinuity, obviously we're not going to be able to integrate continuously from one area to the next. But what we can do is we can integrate around the discontinuity by breaking up the function into pieces around the point of discontinuity. So the pieces that we're going to be determining is going to be right here from 1 to 2, and this area right here from -1 to 0. So we're going to call this one area 1 and this guy area 2. So of course, what is the point of discontinuity for this graph? It was x equals 0. So let's find the area under the curve by hand. So the area of 1 is going to be equal to 1 times 1, which is 1, but it's going to be negative because it's under the x-axis. Okay, so the first area is going to be -1 because it's going to be under the x-axis. And then area 2 is going to be 2 times 1, which is 2, above the x-axis, so it stays positive. So our total area is going to be -1 plus 2, which is 1. So that's going to be our total area for this section. Now, if you find the area under the curve using your calculator, we should get the same thing. So let's see. Menu, calculus, numerical integral from -1 to 2 of control divide. We have absolute value. Nope, that's not going to be it. Oops. Alright, where are we? Here's the absolute value. X in here. And then X down here. Dx equals 1. Now what this is, I have no idea. Questionable accuracy because of the discontinuity. But there's our answer. 1. So when you find it using the calculator, you do get 1. You will get a little sign over here, questionable accuracy, but that's because of the discontinuity. So let's recall, what are the 3 types of discontinuities? So we have a hole, right? So we can have a function that kind of looks like this, from A to B. But somewhere there's a hole, there's a discontinuity. So you basically just ignore the hole and you figure out the area from A to C, and then you figure out the area from C to B, and you sum up those areas, and that will give you the integral from A to B of whatever this function was, dx. So we ignore the whole and then find area 1 plus area 2 equals area total. Alright, step function, we just saw that, where there's a jump. Okay, we just saw an example of that, so I don't need to draw that out again. And then we have the last one is an asymptote. So, one thing that we do have to know about an asymptote, and let's recall what that looks like. Here's A, here's B. So if we were to take the area from A to B, this would work just fine. But what if here's the asymptote and we wanted to integrate to C? So unfortunately, this is the one area where we cannot integrate next to an asymptote. So this is let's call the asymptote B, okay? And let's see, this is not integrable next to the asymptote. And we'll talk about that a little bit later. But you cannot integrate. So you cannot do the integral from A to C for this. Okay, it's not possible. Okay. All right, that basically takes care of it does take care of the rest of section 2. So we'll talk more about section 2 homework, but if you guys did want to do some extra practice, I do recommend that you do on page 266, number 2 and number 3, number 23 and 17. Alright, so I'm just going to put that over here. On page 266, maybe do number 2 and 3, and number 17 and number 23 as added practice. These were the ones that a lot of people had some questions about in previous years, and I know the homework is long and it's about the calculator, but that's more than enough. Along with the College Board assignment that will be coming up shortly. All right, good luck.